Now we are going to start with another theory based on the quantum mechanics. Like we did the valence bond theory, so now we are going to start with another which will describe the formation of the molecule and just make us aware of the molecular orbitals. So that theory is just the molecular orbital theory. Right. So actually you know that see when we have seen the atoms possess the orbitals, you all know that, right. So what happens in atoms, electrons are present in atomic orbitals. In atoms, electrons are present in atomic orbitals, and we also know that when atoms combine, suppose I have one atom, this is my one atom, and when this one atom is going to combine, definitely it is going to form a molecule. And now like the electrons of the atomic orbital, electron of the atomic orbital, now they enter into a molecule. And here we don't use the word atomic orbital, and now we use the word as molecular orbital. So that means when we talk about atoms, we say that electrons are present in atomic orbitals, right. But when we talk about molecule, because molecule is actually formed by combination of atomic orbitals. So when we talk of molecules, we say that electrons are in molecular orbitals. See, and as we have seen that as the atomic orbitals differ in size, they differ in shapes, or you can say differ in symmetry. So likewise the molecular orbital also differ in the the shape, symmetry and this kind of thing, right. So that means now we are going to start with the molecular orbital, so the molecular orbital theory. So as you can see that in this what we get to see that in this there is one atom, this is one atom, it is an atomic orbital, it will combine to form this molecule, right. So now this molecule will behave as one piece, and in this the electrons are present in a molecular orbital. Like in atom it was in the atomic orbital, here it is present in the molecular orbital. As you can see that here there is one nuclei there in atomic orbitals, and here also it is under the influence of one nuclei, but here it is multinucleated, that means it possesses more than one nucleus, right. So this is what is the molecular orbital theory, and you know that as we can write the electronic configuration for the atomic orbitals, likewise we can write the electronic configuration for the molecular orbitals. The same way we will follow the same principles, that is the off-Bohr, that means the orbital with the lower energy is filled first and then those filling occur, successive filling occur. Second, the Hund rules, that you all know that the electron pairing won't take place until and unless each orbital is of same energy, singly filled. Third, the Pauli's exclusive principle, that an orbital can accommodate maximum of 2 electrons and that must be of opposite spin. So all these three rules which we used to follow in atomic structure while writing the configuration for atomic orbitals, the same rule which we will be following when we will write the configuration for molecular orbital, right. So we are just going to do that, but before telling you, I just want to tell you that molecular orbital is actually divided into two types. Molecular orbital is divided into two types. Like as we know that they differ in the energy, they differ in the symmetry. So likewise we say that depending upon those factors, it is divided into two types. We have bonding molecular orbital and we have anti-bonding molecular orbital. Now what is the reason that we classify the molecular orbital as bonding and anti-bonding? The reason is very simple. See, we when we were discussing the quantum mechanics and all, we studied that the electron behave as a wave when it is moving, so that means it possesses a wave function, and wave function is given by psi, right. So we know that the wave can be in phase and wave can not be in phase, right. So that means there can be a constructive interference and there can be a destructive interference, anything can happen, right. So that means for constructive interference, that means we need to add 2 psi. Like that means if I have the atomic orbital 1 with the wave function xi1, I have the atomic orbital 2 with this wave function xi2. So it is possible that these two electron clouds may add up, right. That means it is a constructive interference. So when these wave function add up, so they give rise to a bonding molecular orbital. They give rise to a bonding molecular orbital, and when the two atomic orbitals do not lie in a phase, they are actually out of phase, we can say, or it is a destructive interference, then this is called you can say the molecular orbital formed is called as anti-bonding molecular orbital. So that means we can have depending upon their combination, that whether their wave functions are adding or whether their wave functions are subtracting. So we have two kinds of orbitals, one is the bonding, another is the anti-bonding, right. So like as I told you that by constructive interference what we get is bonding, and by destructive interference what we get is anti-bonding, right. So if we talk about the energies, so what happens, see this bonding orbital possess less energy. Less energy corresponds to maximum stability. And if we talk about anti-bonding, it possesses comparatively high energy. So it is less stable. You have to keep in mind these two things, that when we add the wave functions, it give, or when there is a constructive interference, it gives rise to a bonding molecular orbital. And when we subtract the wave function, that means it is a destructive interference. We need to the orbitals formed will be anti-bonding. We need to subtract them, right? So it is just going to have an impact on the bond. Obviously, it is going to have an impact because the bonding is formed by the addition of wave function, right? And when we add them, so what happens? There is a constructive interference, there you can say they correspond to more attraction, or you can say there is less energy, and we know that less energy is something corresponds to maximum stability. Keep this in mind whenever you are studying in chemistry. Keep in mind less energy corresponds to a state of maximum stability, and everything in the universe is just running behind the stability, me, you, things around, everything, right? So that means the bonding orbitals, because they are formed by addition, so that means they possess less energy and maximum stability. But if we talk about anti-bonding, it is actually due to a destructive interference, so they are formed by subtracting the wave functions. So that means they possess, their repulsion is more comparatively, so they possess high energy and less stability, right. So now I am just going to show you that how the bonding and anti-bonding molecular orbitals are formed. We will follow the same rule of overlapping like as we did, that the bond formed can be sigma and pi, that is end-to-end overlap or sidewise overlap, we discussed in the valence bond theory, right. So we are going to follow the same rule that is universally accepted, right. There is no change in that. So the only thing, the only difference is that here we need to form a molecular orbital. We are talking of molecular orbital, and there we were talking of atomic orbital. The difference lies only in that, right? Otherwise, the overlapping is same, and even the energy factor is same, and even the xi is same. The only difference lies whether we are subtracting the xi or whether we are adding the xi, so that we can get a constructive or a destructive interference. So as we discussed in previous topic, that when the sigma bond is formed, the combination, when we want to combine different orbitals, there are certain limitations, right. That means they should, they should be symmetrical around internuclear axis. So on the basis of that, I told you in a previous topic that only a few combinations are possible, right. Whether the SS can combine, I write here, SS can combine, SP can combine, and PP can combine. Only 3 kind of combinations are possible if we need to form a sigma bond. So here also I am just going to form a sigma bond. The only difference is that, like in one case I will be adding the electron clouds, or you can say I will be adding the xi wave functions, and in one I will be subtracting, right. So this is what, see at the board, this is my S, let us say it is 1s, right. So similarly this is also 1s. So I can add their wave functions, and even I can subtract their wave functions. Suppose I am adding them. So if I add them, so what is going to happen? Nothing is going to get subtracted. They will have a attraction, less energy and maximum stability. So we give rise to this orbital. So as it is formed by end-to-end overlap, so we will say that the bond is sigma, right. And which orbital? 1s, right. So this is 1s because there is an attraction, so it will just add up to give a result. But when we subtract them, suppose this is 1s and 1s, I am subtracting their wave function. So that means they will try to repel each other. So they will repel in such a form that you can see that electrons are pushed towards this side and its electron pushed towards that side. That means they are maximum distance apart. So this region is something called as node. This region is called as node, where the repulsion is maximum and where the probability of finding the electron is absolutely 0. And now if I talk about this bond, so obviously it was trying to do a end-to-end overlap, so that means it is again a sigma bond. 1s is my orbital, but it is formed by the subtraction. It is formed by the subtraction, and we know that the bond which is formed by the subtraction of wave function is nothing but anti-bonding. So you need to put asterisk sign. Just this asterisk sign will indicate that which is bonding and which is anti-bonding. Like in bonding I didn't put any sign, so in anti-bonding you need to put a sign of asterisk, right. So this is my sigma 1s and this is my sigma 1s star, I will say that. And you know that, like if I talk about their stability or energy, so you can see that here everything is adding up, so that means here is an attraction, but here two electron clouds are just repelling each other, so that means there is a repulsion, right. So attraction leads to lowering of energy and repulsion leads to increase in energy. So that means this my sigma 1s is comparatively stable and this is comparatively less stable. I think you got it, that just you need what you have to do is just to add the orbitals or to subtract the orbitals and you will get a different type of combination. Like I just added it, so everything just added to it, there was no repulsion. But here when I subtract the electron cloud, so you can see that electrons are pushed on the corner side and here it creates a node where the probability is 0 and it is nothing but only an anti-bonding molecular orbital that possess the higher energy and least less stability. So this is what I'll just have to do if you need to draw a sigma bond indicating by the s orbitals. Now let's see the another combination, that is the pp. So this is my 2p and this is my 2p. You will know that if I need to form a sigma bond, there should be end to end or I can say head to head overlapping. So that means they will overlap in such a way. They will overlap in such a way. So now here everything is going to add up. So that means this overlapping region is not going to subtract, it is going to add up. So when it adds up, what happened? This electron cloud comparatively becomes big because they both fuse. So this is my result. This is my result. So obviously it is formed of end to end overlap. So that means it is my sigma bond. So whether I have to put asterisk sign or not? No, you are right, we do not have to put that asterisk sign because asterisk sign is indicated when the wave functions are subtracted. So, but here what I am doing is I am adding them, right. So, you do not need to put any asterisk sign because it corresponds to a bonding molecular orbital. So, this is my bonding molecular orbital. So, now let us make the anti-bonding one for 2p. So, this is my 2p and this is again my 2p, and when they just try to overlap, they overlap in the same way. But here what we need to do is we need to subtract this, we need to subtract. So that means subtract means there will be a repulsion, it will give rise to a structure like this, and what is this? This is the node where probability of finding the electron is absolutely 0. So as it is formed by end to end overlap, again it is a sigma bond, 2p is my orbital. But it is formed by subtracting, as you saw that I just subtracted the electron clouds. So that means it is not a bonding one, it is a anti-bonding one. And how we denote the anti-bonding? With an asterisk sign, right. So this is my sigma 2p and sigma 2p star. And now if we talk about energies, like we talk energies for the 1s orbitals, so similarly the bonding orbital is always going to possess less energy, because here it indicates an attraction, right, everything is just adding up. But here what we see that here the energy is more. So that means more stability for bonding and less stability for anti-bonding. So this is how you have to make the sigma bond for the 2p orbitals. So what you need to do is just draw an atomic orbital, try a positive combination, try a negative combination, and when they will overlap, so when there is additive one, so just add that overlap. But when there is a subtraction, that if you need to subtract, just subtract that overlapping region and you will get the result, right. So it's not a big deal, just draw the figures, try it out, you can easily do that. So now this was my sigma bond. Now we'll try for the pi bond. So just look at the board, okay.